The topic of the lecture is Structure of Polymers. The reference textbook is Richard Van Root, Introduction to Dental Material, 4th edition, from page 23 to 30. Polymers are highly versatile materials in that they can be solid or liquid, brittle or flexible at body temperature, depending on their composition and configuration. The starting material of a polymer is called monomer. Polymers are long chain molecules consisting of many repeating units. Agar, cellulose, and DNA are naturally occurring, while polyvinyl chloride, polyethylene, and nylon are synthetic. A polymer with similar structure to polyethylene is polypropylene. It is formed by joining molecules of propylene. In the figure B, propylene differs from the ethylene in having a methyl group, CH3, that replaces one of the hydrogen atoms, forming the polymer polypropylene. Polypropylene differs from polyethylene in the arrangement of the methyl group, in which they are isotactic, which means all in one site, syntactic, alternate from side to side, and atactic, are switched from side to side in a random manner. As I mentioned, the starting material of polymer is called monomer. So in this figure, the polyethylene in A is derived from the ethylene which is in B. The most common polymers are those made from the organic compound with carbon. But polymers can also be made from inorganic compound based on silica. An example of a silicon-based polymer is polydimethylsiloxane, which is shown in this figure. So here is some of the common polymers and monomers. We have polyvinyl chloride, polytetrafluoroethylene, polypropylene isotactic, polyacrylic acid, and polymethyl methacrylate. Types of polymers: we have homopolymers and heteropolymers. Homopolymers, when a polymer is formed from a single species of a monomer. And heteropolymers, when different species are included. Mechanisms of polymerization. Polymerization is the process of preparing polymers from monomers, and it's done in two mechanisms, which are addition polymerization and condensation polymerization. Addition polymerization occurs when the reaction between two molecules, either the same to form a homopolymer or dissimilar to form a heteropolymer, produces a large molecule without the elimination of a smaller molecule, byproduct. The stages of the addition polymerization: activation, initiation, propagation, and termination. Activation is the process of producing free radicals. Free radicals are very reactive chemical species with unpaired electrons. Initiator, which is phenyl, are able to initiate vinyl polymerization. For initiation to occur, an activator is achieved by decomposition of peroxide. Activation can be induced by any of the following methods: by heat, more than 65 degrees for benzoyl peroxide; chemical compound, tertiary amine; and by light, we have ultraviolet or visible light with benzoyl methyl ether or alpha-decetone. Benzoyl peroxide is activated by a tertiary amine, which is biochemical activator. Initiation. Free radicals react with monomer and initiate polymerization process. Propagation. Free radicals are transferred to the monomer, which can in turn react with another monomer. Process is repeated again and again, generates polymer chain until growing chains colloid or all radicals have reacted. Termination. Free radicals can react to form a stable molecule. N will vary from chain to another. A wide range of long-chain molecules are produced. Some unreacted monomer and some oligomers can form. Condensation polymerization occurs when two molecules react to form a larger molecule, not usually the same. With the elimination of a smaller molecule, byproduct is formed. The byproduct is usually water or alcohol, accompanied by shrinkage. In this case, monomer units with a carbon-carbon double bond are not necessary, as shown in the following example of a silicon, which is an inorganic polymer formed by condensation of silicon. Chain configurations. Chains are held together by secondary bonds or van der Waals. The higher the molecular weight, the stronger the polymer. On cooling, the bonds are re-established and the polymer becomes hard again, retaining the shape it was in the higher temperature. The temperature at which a plastic softens such that the molecule can begin to flow is defined as its glass transition temperature. Crystallinity in polymers. In a polymer, the molecules usually twist and turn, coil up and crisscross in a random fashion. Sometimes, however, there will be zones where the molecule will lie or be less parallel to each other. When this happens, crystallinity will exhibit. The crystalline and the non-crystalline region in a polymer depends on the chemical composition. Cross-linking. When chains are linked together by chemical bonds, the polymer is said to be cross-linked. This cross-linking can make the difference between a thermoplastic polymer and a thermosetting polymer. More importantly, it can convert a liquid polymer into a solid polymer. This process is used in a setting of many impression materials.